Hey folks, let me start with a demo. So if you're here and you're on your laptop or you're on Zoom or in Paris, head to this link. I want to just show you the kind of models that we build at Galaxy Zoo. So Galaxy Zoo, if you haven't heard of it, it's a crowdsourcing project. We recruit hundreds of thousands of citizen scientists to measure the morphology of galaxies. We just show them the galaxy, ask them what's in the picture, classic supervised learning setup. It looks like this, the demo. So we can take the galaxies from decals or now DESI and filter them by the predictions of our deep learning models. So for example, here I'm filtering for galaxies which have spiral arms, which have 2 spiral arms, where they're loose wound. Please play around and see what you find. Now, many people here are cosmologists. Maybe you don't get a bed for anything smaller than the field. For me, I want to understand why galaxies look the way they do, but I hope maybe the principles behind building those models might translate, and that's what I'm going to talk about in this talk. So the first principle I want to talk about is multitask learning. So in that demo, that wasn't a different model predicting the answer for each morphology question. It was the same model predicting all the answers for all the questions in one forward pass. And that's really important because it changes the internal representation the model learns. And you can show this through a fine-tuning test. So let's say, in this case, I want to find ringed galaxies, which is not a question that Galaxy Zoo asks. On the x-axis, this is how many sort of downstream test galaxies I'm trying to search for, the ringed galaxies that I have for fine-tuning. And you can see that if I train the same model only to predict the smooth or featured top-level Galaxy Zoo task, I have to fine-tune deeper and deeper into the network to get the performance to work well. But if I train a model on all the tasks, and then I ask, how many ring galaxies do I need to fine-tune and how many layers do I need to adapt? I don't need to adapt any layers. I only need a linear fine-tuning to say, from this representation, tell me where the ring galaxies are. Another demo, if you'll indulge me. You can play around in this latent space. And I put this because we had that debate yesterday about where is truth in latent space. And this is the kind of truth that we find in our models. What you can do on this demo is you can click around at a point in latent space, and it will simply query for galaxies near that point in representation space. So you can, for example, click over here and find galaxies which have quite obvious low surface brightness stellar streams. Or you could click down here and you find sort of clumpy, dwarf, irregular galaxies. So this is kind of, I think, building a bit on Francois' point in the debate that models can learn to put similar galaxies in similar places in representation space. But A, that's not a self-supervised feature. This is a purely supervised problem. And B, the reason it works is because of that multitask training. If you can answer 140 Galaxy Zoo questions, you can do 141 with very little extra effort. And just to flash up, here's a bunch of people who've been using the models are all public, the code's available, you can fine tune them for your own galaxy image problems. And just to say, go to this GitHub link if you want to try it. That's a complete example. Multitask learning was important to us because the Galaxy Zoo labels, you might think, Mike, why are you giving a talk about label efficient learning at Galaxy Zoo? You have all these volunteers, and those models were trained on something like 105 million volunteer clicks. The reason we still have to be efficient is more data is better, and modern architectures are incredibly data hungry. So there's been a lot of excitement about transformers, for example. And a lot of people say, Mike, sometimes you call your models foundation models in that they're, pre-trained on a diverse source and fine-tuned, but they're tiny. Come on, they're not really foundation models. Have you not tried making them bigger? And of course I've tried making them bigger. It doesn't work. And here is the proof. I'm showing CNNs in blue, transformers in orange. I'm making the models bigger this way and consistent with the error bars, which are just the per batch validation loss variation. So the same model with a different batch, there is really no difference in making models bigger or really fancier. Ponder that one for a minute. I think the reason is because transformers especially lack the kind of inductive bias of CNNs. You really need a lot of data. And in the CS world of big models, they're talking about 300 million, a billion images. For GPT, vastly more language tokens. So actually the astronomy world is small data versus that. A few ideas for how to sort of exploit our labels better. Contrastive learning, this is bootstrap your own latent, is quite effective. So you take two versions of the same model have one predict the other, create a contrastive representation. A colleague, Inigo Val, did this for Radio Galaxy Zoo. His context was trying to find the specific class of Fahrenhof-Rayleigh type 1, type 2 radio galaxies. And he's working in this small data regime. So you have only a few hundred labels. And he found that contrastive pre-training helped him solve that supervised task much better. We can do the same thing for Galaxy Zoo, but we need to add something. So we add this extra classification head onto one of our two models. And so we jointly solve both the supervised task and the contrastive task. And they guide each other to do better than either alone. And just to flash up the results from that, in the black dashed line is sort of training from scratch. In the green line is the multitask pre-training. In the orange line is this hybrid bootstrap your own latent approach, where again, we need fewer and fewer labels to do well. And just to flash up what we're doing next, this is some really new work by a colleague, Michael Bowles. He's working on using masked autoencoders, another kind of self-supervised learning approach. You can kind of see here, you mask some of the image and have the model recover what's left. But his twist is that for galaxy images, this works very poorly. And it works really poorly because like most of the information's here, right? It's not going to tell you a whole lot if you'd mask that out. So it turns out this works much better, he's discovered, if you mask in Fourier space, where you're masking the different scales in the image. So please check that out when it comes out in a few months. And Mike is also on the job market. Please hire. Lastly, I want to talk about just like reframing the problem. So Galaxy Zoo has historically been about classifying galaxies. But if we were to start again with the knowledge that we could fine-tune models on little labeled data, say, and we also knew the kind of CS computer vision stuff that would come out, maybe classification is just not the task that we would want Galaxy Zoo to do these days. Why don't we think a little more creatively? So something that I did very recently, and you can see it at the NeurIPS ML4Phys workshop in a couple of weeks, is segmentation. So Galaxy Zoo collaborated with Karen Masters and co. Labeled some 27,000 manga galaxies and had volunteers draw bounding boxes around the spiral arms and bars. Turns out we can train just a very normal UNet with a slightly fancy loss to allow for the noisy volunteer labels and do a really good job at predicting where those spiral arms and bars are. Actually much better than not just the kind of standard automated rule-based approach, Sparkfire, but actually better than the original labels. And the reason it's better than the original labels is the original labels are drawn by a polygon bounding box, right? So they're straight edged. But spirals are not straight edged fundamentally. And so the model learns to essentially smooth or interpolate over those hard edged lines to learn a better prediction than the label started with. And just to provide some numbers behind that, we asked 20 independent astronomers to look through a bunch of our galaxies, and they rated our model as better, not just in Sparkfire, but better than the original labels. And if you'd like to try it as well, I won't do another whole demo thing, but the link is there if you don't believe me. The science you can do with this, I think, is exciting, but kind of unclear. So for example, it's very easy to pull out bar measurements from this, like given the mask of where the bar is, just find its extent. And that means it's simple to recover bar lengths at scale, and we find we recover them really just as in very good agreement with a whole dedicated project for measuring bar lengths, just falls out of the masks. But really none of this is about bars or spirals. Like more fundamentally, this is a shift to segmentation tooling, and you could apply the same method for really any kind of galaxy image problem. So although here I've kind of focused on making masks, say, of spirals, and I'm just showing a bunch here, so you believe me that it works mostly. I'm kind of excited that what else should we pull out of images that we wouldn't have thought we should pull out of before? But now we know we can go through this process. What is the target? And so the next thing that I'm building and that I'm really pushing Galaxy Zoo towards is to have an open sort of web-based crowd platform, just like Galaxy Zoo is now, where we have a volunteer crowd to segment things. And other astronomers can create tools for segmentation or segmentation tasks and share their data. We can run the exact same tooling, really. And we can ultimately build these kind of diverse pre-trained segmentation models to deal with surveys like Euclid and Rubin and find stuff like low surface brightness structure, stellar streams, jellyfish tails, whatever kind of detailed components you want in images. I want to help you pull them out. Thanks very much for your time.
All right. So we'll go back to our format where we do one question here, one from Slack, and then one from Paris. So do we have one from here? Yeah, Peter.
Correctly, that you still need the volunteers to see the thing that they're sort of labeling. So it needs to be visually evident in some way before you can tool around the volunteers, right?
Yeah, I think that's true. It's not magic. So we need a hook. Yeah.
But it's also, have you thought of trying, for instance, giving them the residuals of a simple model to kind of dig down further into something that you could not directly see?
Like your dust lane example.
Exactly.
I understand. Yeah, that's a really fun idea. So I think it has to be recognizable in the image. Certainly if you want a supervised fine-tuning step, but the image doesn't have to be a telescope image. It could be a pre-processed any way you like. And another example that I also work with Chime, and we want to do, for example, locate faint fast radio bursts in the waterfall plots. And that's not too hard by eye sometimes, but it's very hard to fit them because it's full of all this other RFI noise. So just saying here is the burst is quite useful. So I think we can be more creative than just optical galaxy images, totally.
Do we have anything in the Slack? Okay. Paris?
I don't see any hand raised, so we don't have question here.
Okay. Any more in New York? Yeah, Sebastian.
Yeah, I'm a little curious, especially for these like segmentation type approaches, like what you see as the final science objective of having this nice segmented map. Because in a lot of those cases, I wonder, like, say you were trying to understand like bar lengths, for example, if it wouldn't be better to just target that directly instead of going through the segmentation step as sort of an intermediary. Like, what are your thoughts on that?
Target it directly, like in contrast, how?
Well, I mean, in the same way that you would like label the data in the same way that you label the segmentation, but presumably the bar length problem is like easier to get a large number of labels for than like good segmentation labels.
I think I'm not sure I see the distinction quite that way. So like in the Manga project, for example, that Karen ran, like there was a two-stage segmentation. They say, draw on the bar, here's a box, draw a bounding box around the spiral. So I think it's not that we're trying to sort of segment everything in the image, say, like we have each segmentation problem has like a specific science target that we're trying to get to. And if bars are your target, then make a tool which is a rectangle and show it to the volunteers and gather that data. I think what I'm kind of pitching is that we should have the same model fundamentally start to solve many of these tasks because they'll inform each other. And I think we'll need to do fewer of the bar drawing if you want to find bars, say. I think in terms of obvious science cases, like just with this alone, say, understanding how star formation rates differ along the length of spiral arms in all of DESI, say, or for IFU surveys like Manga and SAMI, understand the links between morphology and these kind of structures. For LSB science to find that, how do the length of tidal tails relate to time since merger, like Bobby's really cool talk. Like there's just so many possibilities and I'm doing too much CS to really think about it. So please help.
Okay, anything from Paris? Just checking one more time since we have some time.
No, thanks for us.
Okay, well, let's thank Mike one more time for this great talk.